Hey everyone! Today we will be looking at complex numbers, which can be referenced in Section 9 of Chapter 5 from our textbook. So open your notes to a new page, and here we go. The complex number system is made up of real parts and imaginary parts, and will be written in the form a plus bi, as it is right here. Now, a plus bi is made up of a real component a, which is in my real number system, which is the number system that we're used to, and the imaginary component. The imaginary component is bi. That's where we have a real number times the imaginary number I. So all complex numbers are basically the sum of a real component and the imaginary component. Now let's consider operations on the complex number system. Say, for instance, we're adding two complex numbers. This is really no different than adding two binomials in the real system. So what we do is simply combine the two real components, namely 2 and 3. When I combine those together by addition, I get 5. When I combine the two imaginary components, I treat I as a variable, and I add the coefficients of the imaginary part. So I have a negative 3 plus 4 for a grand total of 1i. And just as in variable expressions, we don't bother putting the 1 there. So that's my simplified answer, simply 5 plus I. Subtraction. The thing we want to be careful about with subtraction is to distribute our negative sign through. I'm going to copy down my first complex number and distribute my negative through for my right complex number, which is negative 2 plus 5i. Again, at this point we're just dealing with addition. Combine the two real components for a grand total of negative 1, and the two imaginary components, namely positive 9i. Now, even if we were to rewrite this as 9i minus 1, that would technically be okay, but when we simplify a complex number, we like to have our real component first and then the imaginary component. So I'm going to leave my answer as negative 1 plus 9i. Now let's look at multiplication with complex numbers. Again, when we multiply two complex numbers, it's the same as we would do with regular binomials. We want a FOIL. So let's multiply the two front terms to get our front product. When we do that, we end up with 6 as a result of 1 times 6. The outer product will be negative 2i. The inner product will be positive 24i. And the last product will be 4 times negative 2, which is negative 8, times I squared. Now, it ends up that this product right here turns into a real number, since we know that the equivalent of I squared is negative 1. So, let's go ahead and combine like terms. I'm going to add 6 to 8. Again, this is because we know that negative 8i squared is equivalent to positive 8 as a result of negative 1 being substituted in for I squared. So, our real component of this expression simplifies to 14, and the imaginary component will be negative 2i plus 24i, which is a grand total of positive 22i. So our complex number, 14 plus 22i, is what we get as a result of multiplying two complex numbers together. Okay, division. Since we know that I is equivalent to the square root of negative 1, having I in the denominator is like having a radical in the denominator. And we know we do not like to have radicals in the denominator of a simplified expression. So what we need to do is multiply the top and the bottom of our fraction expression by I in order to eliminate I from the denominator, because we know that I squared is equal to negative 1. So we distribute the I through on the top, and I end up with a 3i plus I squared over 4i squared. Again, since we like to have complex numbers written in the a plus bi form, I'm going to substitute negative 1 in for I squared, and then write 3i on the back. And in the denominator, we have 4i squared. Again, since I squared is equal to negative 1, I'm going to substitute that in for I squared in the denominator, and I get negative 4. Although this is simplified, we could get rid of that negative just to make it look a little bit more organized. So when I take my negative out, I distribute it through on the top, like so. So I end up with positive 1 minus 3i all over 4. Now let's consider a fraction example where we have a binomial or a complex number in the denominator. Now again, since I is equal to the square root of negative 1, I do not want to have I in my denominator. So in order to rationalize the denominator, we want to multiply the top and the bottom of my fraction by its conjugate. Remember, a conjugate is the same binomial where the middle sign is changed to the opposite. So the conjugate of 3 minus 2i is 3 plus 2i. So I multiply the top and the bottom by 3 plus 2i, and I can rationalize my denominator. Let's see what happens. I'm going to distribute my 4i through to the 3 plus 2i, and I end up with 12i plus 8i squared. Remember what happens to the I squared. We'll replace it with negative 1 in the next step. Now let's tackle the denominator. As a result of foiling any binomial to its conjugate, we know that the outer product and the inner product cancels. So let's focus on my front product, the 3 times the 3, here and here. I end up with a 9 in the denominator. The outer and the inner product cancel each other out, and I've got negative 2 times positive 2 for a grand total of 4 times I squared. Again, we know that I squared is equal to negative 1, so let's substitute that in for the numerator and the denominator. So here I end up with negative 8 plus 12i all over 9 plus 4. Again, that's a result of substituting -1 in for I squared, and -1 times -4 gets me positive 4. 9 plus 4 is 13, so we are almost simplified all the way. My final answer will be -8 plus 12i all over 13. All right, let's consider this one last example. Let's find values of x and y to make a statement such as this true. Now what we want to do is rearrange our components so that we can have an equation based on the real values and an equation based on the imaginary coefficients. So let's find the value of x. That would make 7x plus 2 equal to 5. So let's write a miniature equation over here on the side. I'm going to write that 7x plus 2 is equal to 5. Therefore, subtracting 2 from both sides, I end up with 7x equals 3. And then x equals 3/7. That's the value of x that will make this real component equivalent to this real component. Now, y minus 3 is my coefficient of my I on the left side, and 2 is my coefficient of I on the right side. So we're able to simply set these two equal to each other. So that means that y minus 3 equals 2. Add 3 to both sides, and the value of y is 5. Now that we have seen an example of each operation on the complex number system, we may conclude our lesson on the complex numbers.
Made with Doodlecast Pro.